Alright, so we're going to begin by talking about our conic sections, and one of our conic sections is the equation of a circle. And this is our general form for equation of a circle. You can see x minus h squared plus y minus k squared, and then equals our radius squared. And so the key component is that we are subtracting those values. So if my center is at 3 and negative 2, and my radius is 6, I'm going to plug those values in. When I plug a negative 2 into subtraction, it becomes a positive value, and that's that 36 there. And we can make it look a little bit more what's going to become like our equation of an ellipse by setting equal to 1, just dividing by 36 as we go forward. So this is our ellipse. This is going to allow us to find our foci as we move forward. So basically we have these two focal points that are inside of our ellipse, and we have a major and a minor axis where the major axis is A and the minor axis is B. We have some center H and K, and we have our equation here, which is very similar to the equation of a circle, except A and B don't have to be the same value, and it's going to be equal to 1. But the center points work exactly like the circle worked. Our other one is our hyperbola, and we again have our focal points here, except it's not quite the same as we had previously. We have a couple of options. We can just memorize this slope formula for our pieces, or what we can realize is we just know that A is attached to X in this direction, and B is attached to Y, so it goes up. And if we have our values there, we can go up and down B over A, and then make this box, right? And then the diagonals of that rectangle give us the correct slope as we move forward. So same thing here. You could go, again, A is attached to Y as it's here, and so we'd go up A and then over B. We'd make a rectangle, and we could put our asymptotes within there. So that would be the box. Those become your asymptotes, and it'll be easier than trying to remember where these things come from that way. All right. So there's a hyperbola. We've done the circle. We've done the ellipse. And how it's usually going to look is an equation like this. So we have some equation where we have an x squared and a y squared term, and we need to put it into one of our kind of standard equations. And we do that by completing the square. So if we take one of our equations and we group our terms together, where we have our x's and our y's together, we're trying to find this missing component so that we can factor it. And the reason why it's called completing the square is I have an x squared term that goes there. I take half of this value, half of the 8, and I put it on both sides, 4x, 4x. What's missing in order to complete the square is this piece here, which if we were to just label the sides of our square, has to be 16. So if I add 16 to that side, I'm going to have a perfect square, which is x minus 4 times x minus 4. But I need to add 16 to the other side too in order to keep my equation balanced. So I do the same thing with y, except I'm going to factor out that 5 in front of it, and I have my x squared, my 3x, 3x, and what I'm missing is the 9. However, when I add 9 to that side, I don't want to just add 9 because that 9 was actually also multiplied by 5. So what I really need to do is take that and add 45. So now I've got it into my equation, right? I'm starting to make it look more like the equation of an ellipse. And I set that equal to 1, and I get x minus 4 squared, y minus 3 squared, over 100, and then over 20 equals 1. So that's an ellipse. And I can see I have a major axis and a minor axis, and I can start to graph that if I need to. So if I was to graph it, I'd find the center, and from the center I can start to put the major and the minor axes on there. So A is 10, B is the square root of 20, and I have my equation for my center, and I start to graph it. So there's my center point, 4 and 3. I go over 10 as that's attached to x. That's my major axis, and I go up 4.5-ish because that's my minor axis. And then I could find those points in blue. Those are my intercepts. And I just do that by setting the appropriate value, either x or y equal to 0. So if I want an x-intercept, y is 0. If I want a y-intercept, x is 0. And you can solve and get a more accurate sketch for our pieces there if we need something that's a little more accurate. All right. And again, this is just solving for your intercepts, and it's a good check to make sure that things are right around where we think they should be. So like 11.4, negative 3.4, And again, this is a rough sketch, but that makes sense for what we have as our picture. The y-intercept, same thing, x is 0, and go from there. Alright, we have our other one. I'll go through it a little bit quicker. What conic section is it? And then graph it, and we factor it, same as before. We'll pull out the 5 and the 4. We're looking to complete the square. I take half of the 8 and square it, half of the 4 and square it, and then I just make sure that I add the same thing to both sides, and that will keep things balanced. And then it's just algebra at that point. I'm dividing through, and I can see that I have subtraction, which means it's going to be a hyperbola. And now I have to look at which direction it's going to go. That's going to be the hardest piece, as to does it go up and down or does it go left and right. And as we start to sketch it, we can put our pieces in. And so I have my center point, which is 4, -2. And then my a value, because that comes first, again for the hyperbola, it's going to be the first value. So I go out 4.5, and then I have my vertices there. And then my b value, as I go up 5, there's my rectangle for my asymptotes. And then the graph is going to look like that. And that's going to be my pieces. And again, I know that it goes that way as A is along the major axis and it's attached to X. And I could get my intercepts again by looking at X. For this case, my X-intercepts are Y is equal to 0, and I can solve for there and get my equation, get my points. And I get some value that's close to what we're looking at. Alright, our last conic here that we're going to worry about is our parabola. And this equation is a little bit different, as it has a set of all points equidistant from a directrix, which is a fixed line. For right now, it's just going to be either horizontal or vertical. We'll deal with rotation down the road. But if I have a vertical directrix, I have an x squared term, and I'm looking for this thing where I have this p value attached to y. So 4 times p is going to be the distance from the vertex to the focus and from the vertex to this line of the directrix. And that's going to help me graph these as I move forward. So if I have an equation that looks like this, I can see right off the bat this is a y squared term, right? And so there's no x squared, so it's going to have to be a parabola. And I'm going to have to put it into the form that I look at. So I'm going to put it in standard form, and then I'm going to graph it. So y squared plus 10y, again I'm going to take half of the 10 and square it, which is 25, add that to both sides, and then I get my value, and it's my standard form. Right, that's what I'm looking for. That's the first part, and I can see that this -4 is in the place of 4p. So I set those equal to each other. There's my vertex. 4p is -4, p is -1, which means there's my vertex, and then I go to the left by p, and then I add a -p, and that's my directrix, and then my x-intercept would be up at y equals 0, and I can solve for it, and I get a value of -7.25, and it goes like that. Alright, so again, you got to be careful of how this works. We add that p value. If p is negative, it's the same as subtracting it. In this case, when p was negative, it went over here to that side.